Hello, everyone. Welcome to the 2025 PIBBSS Symposium. Our speaker, Dalcy, will be talking about the local geometry in RL policies.
My talk is called Correspondence Between Local Geometry and Control Policy, or a catchier title is the name Structural Bayesianism for Control. So I'll start with some motivation for why one should care about this. So I'm interested in selection theorems, which I believe is a notion introduced by John Wentworth, which is a class of theorems that talk about convergent properties of systems that are selected under a certain selection criteria. With examples being like coherence theorems, which are also a class of theorems like VNM or Savage or Jeffrey Bolker and so on. And for example, VNM states that given that a system has preferences over lotteries that satisfy certain axioms like completeness or transitivity, it states that the system's preferences can be represented as if it's assigning a utility to each of these lotteries and comparing the value. And those axioms in turn can often be justified on Dutch book grounds, which says that if your preferences do not satisfy these axioms, then it can be exploited by an adversary and be money pumped. So broadly speaking, the coherence theorems can be kind of thought as if your system is selected for coherence for some reason, then the conversion property of those systems is that it behaves like a utility maximizer in saying it kind of like imprecisely. And another example is kind of like many variants on good regulator theorem, which pretty much says that a regulator that is selected to minimize the entropy of a variable is behaviorally equivalent to a deterministic function of that variable. So we care about selection theorems because essentially, we care about it for alignment purposes because essentially, the learning machines and agents that we produce by, say, like training are kind of very particular kinds of systems that are selected pretty heavily for certain criteria, like, say, low loss. So if we can have a theorem that says something about the kind of systems that that are selected under such criteria, then that'd be pretty interesting. But I want to focus, or at least my motivation is on a more particular kind of selection theorem, which talks about internal structure or structural selection theorem. Because one thing to observe about these theorems is that they're all about kind of behavioral equivalence. Like say, like one of the common misconceptions of like coherence theorems like VNM is that uh, one might think that it says that if your preferences satisfy these axioms, then one must say internally, like algorithmically be tracking the utility variable and making decisions in terms of that. But it does not say that, importantly, and it only talks about behavioral equivalence, that it can be represented as a utility maximizer, but it doesn't have to be a utility maximizer, which is a pretty important distinction. And we care about internal structure because it could give like some coherent, like some concrete knobs to turn the system. So, like an example of a structural selection theorem that is often talked about in the alignment literature is the agent-like structure problem, which I also believe is originated from John Wentworth or Scott Garbrand, I think, and which broadly speaking says that, or at least wants to say something like well-performing agents are in some sense internally organized into certain modular structures like a internal world model and a search process. And this is a very precise claim about the internal structure or the algorithmic structure. And if it tells us how this internal world model is organized or related to the search process, then we can use that to actually find those systems in these like real world systems to help with alignment and so on. So that's one reason why I'm interested in structural selection theorem. And also another reason is it can tell things about like how a given model would generalize. Like given two equally performant solutions, is this memorization or is this like actually learning like an intelligent algorithm, which is also a claim about internals. So that's a motivation. But the issue is that there's not really a lot of, or at least like, or let alone like any example that I can really think of like a very good structural selection theorem. And the main bottleneck, I think, is because how do we even get a theoretical handle on the notion of internal structure to the extent that we can prove these theorems about it? And the second problem being, if we do have such a handle, then how do we actually show that this structure is being selected for under some selection criteria that we care about, like training or evolution? And I think there is now a plausible answer to each of these questions, such that when combined, they could provide a structural selection theorem. And I believe the answer to the first question is something called a structural Bayesianism. And the second question is singular learning theory. So I'll explain each very briefly in turn and explain why I believe that. Okay, so structural Bayesianism is a notion introduced by my mentor Dan Murfitt in his paper with his student called Program the Singularities. And it's a thesis that there is a correspondence between internal structure of a program and the local geometry of some potential that the program is embedded as a critical point of. So I'll explain that further. So it's better to think of this in the case of a neural network. So structural Bayesianism is the thesis that the internal structure of a neural network, like the high-level algorithms that it implements, and the local geometry of the loss function for which the neural network is a critical point of, say like a local minima, it says that the internal structure of this neural network is in correspondence with certain properties of the local geometry of the loss potential. So why expect this to be the case? Well, like there's like several variants of this that are a bit more commonly known in the wider deep learning theory literature, like notions like Bayesian broadness. Like Bayesian broadness is often related to properties of the neural network, like robustness, and that's an example of such a correspondence. But structural Bayesianism is kind of a thesis that we should take this correspondence like much more seriously, and that we should expect there to be subtle information about the internal structure of neural networks to be revealed from the local geometry. And just to note, this thesis is kind of the word thesis in the sense that the Church-Turing thesis is a thesis. Like it's not a precise theorem per se, because it involves a intuitive concept of internal structure, where in the case of Church-Turing, like the computable program. But rather, its correctness is something to be verified over time after like many demonstrations of such correspondence actually holding in practice. So, structural Bayesianism, I think it has the potential to give such a handle on internal structure by providing this dictionary between that and the lost geometry. So, and the second part of the puzzle is singular learning theory, I think. And I am not going to explain it in detail, but the only thing important is the last line here, which at a high level, SLT is kind of like is a theory of is an asymptotic theory of Bayesian statistical learning. And at a high level, it tells us how different solutions to a learning problem should be differentially favored depending on their local geometry and some potential, and the potential here being the Kale divergence. So it relates the local geometry of the solution with the degree to which those solutions get selected for, which is a very high, which is the high level way of putting it. So structural Bayesianism is the thing that'll give us a theoretical handle on the notion of internal structure by relating it to local geometry. And singular learning theory will then tell us which of these local geometries are more favored or more selected in the specific selection criteria of Bayesian learning. So I believe these combined can give a potential path towards proving a non-trivial structural selection theorem, which I think is the main reason for I'm interested in this. So, this talk will be focusing on the first part of this two-part thing, where we want to investigate structural Bayesianism specifically for in the context of control. By control, I mean things like MVP and so on. So the goal is to investigate the correspondence between the structure of a control policy pi that is parameterized by some data and the local geometry of the control loss, which would be the expected cumulative reward landscape of the MDP. So I hope that made sense so far. And please, if there's any question, feel free to ask them. So let's set some notation first. So an MDP is a tuple that consists of a bunch of states and actions that you can take. And the MDP's transition kernel P is a map that takes the current state and the action you take, and it returns the distribution over states. So it's kind of like an environment. And the reward function is a stochastic map that takes the current state and returns a distribution over numbers. And gamma is discount factor, which I'll talk about later. And lambda being the initial state distribution. So that is the MDP, or the world of the control problem. And the second part is the policy, which is a map from the current state to the action to a distribution over actions that assigns a probability distribution over actions. And these two combined will induce a distribution over trajectories, which is a pair of state action tuples under this formula. And denoting the expectation taken under this distribution as E of pi, the objective of the control problem, dynamic programming, whatever, is to find a policy pi, again, a map from states to distribution over actions, that maximizes the expected discounted return. And in particular, we'll be considering policies that are parameterized, which means that there is some set of parameters that we're going to consider, like some subset of Rd, where D is the number of parameters. And we'll assume that there is some parameter function map that assigns a policy to each of the parameter configuration. Like imagine this to be like a neural network. So the potential that we'll be investigating is J of theta, which is J of pi theta. So the question we'll be asking is, given a critical point, you can actually just think of this as like a local minima, or for the examples that I'll be showing later in the slides, it's actually just a global minima. Oh, sorry, local maxima and a global maxima, because it's MDP, it's control, so like higher values are better, unlike the loss. So given a critical point theta star of J theta, the question is whether the local geometry, in some sense, of J of theta at theta star, can it say anything about the internal structure or qualitative properties of the policy pi theta star that it implements? So that is the question that will be motivating us. And to verify this, we'll come up with various toy models that, at least in very specific cases, validate this thesis. And we'll see if there are any like generalizable insights that we could extract from those toy models beyond the specific setting. So the first example is the two-state model, which is kind of the simplest setting you can consider, where you have two states, S1 and S2, and you have two actions you can take, up and down, and they behave in the way, like the obvious way. Like if you take up at S1, then you stay put in the same state. If you do up at S2, then you move from S2 to S1. And if you move down at S2, then you stay put, and if you move up at S2, then you move to S1. So it's kind of the obvious way. And the initial state distribution is S2, so you start at the bottom state. Actually, there's a caveat here that the transition probability of going up and down in the way you would expect actually has a slight chance of your kind of like your hand perturbing and accidentally choosing the wrong action. So there's epsilon, which is kind of like an external noise. But for now, we'll be setting epsilon to 0, so this is a perfectly deterministic environment. And the policy is essentially a tabular policy where the theta 1 and theta 2 each represent the probability of going up at state S1 and S2. So theta 1 is a probability of going up when you're at S1, and theta 2 is a probability of going up when you're at S2. So obviously, the optimal policy here is to just choose a policy that goes down forever, because you start at, oh, sorry, and I forgot to mention that the reward of the MDP is that you always receive a reward when you're at the bottom state, and you continue like that for forever. So the obvious optimal policy here is to just kind of move downwards all the time, because you start at the rewarding state. And so if you keep moving downwards, then you stay put at the same rewarding state forever. So that's obviously the optimal policy, which means that the optimum policy is kind of like a line where theta 2 is equal to 0. And because you never actually enter the top state S1, theta 1 is kind of like a free variable, and it doesn't matter what value you choose for it. But the important thing to notice is that even though these are all kind of equally optimal policies under the eye of the under the lens of the value of J they take on, they're intuitively implementing a qualitatively different policy. So, for example, you start at S2 and you always move downwards, but say for some like whatever reason you're accidentally put on state S1 for which is actually impossible when epsilon 0, but say that you went to S1. Then because S1 because theta 1 is 1, it means that you will move up here. So if you accidentally misstep and move to S1, then you'll be stuck in the non-rewarding state forever. So this is kind of like a very fragile policy. While in contrast, if theta 1 is 0, then if for some reason you ever move to this S1 state, then you'll immediately recover or error correct by going to the rewarding state again. So this is a very robust policy. And there's kind of like a continuum of this uh, as you interpolate between 1 and 0 for theta 1. But again, they all get the same reward because epsilon is equal to 0, so the actions are deterministic. So the values of J cannot distinguish between these policies with different degrees of robustness to some extent, in some intuitive sense. So the question of interest is whether they can be distinguished in terms of their local geometry. And just as a remark, um, the way to think about epsilon here conceptually is kind of like a okay, so epsilon is equal to 0 kind of represents the environment or that we have like empirical access to. So it's like an in distribution setting. So J0 is the kind of is the lost landscape that we actually have empirical access to, or that's at least the story that we're trying to tell. And for J epsilon, where epsilon is greater than 0, those are environments that are out of distribution. So kind of by definition, we don't have empirical access to them. So that thing that we want to show is that we can actually extract properties relating to epsilon by only using the potential J0. So can we use the local geometry of J0 to say something about the robustness? And can we operationalize this? So this is one specific operationalization of this idea. So given theta star, which is a critical point of J0, we define epsilon star as a value that solves the following equation for some value of alpha, which intuitively represents the degree of perturbation that a policy is robust, perturbation that a given policy is robust against. So it basically says that, so theta star is a critical point, I'll just say a local maximum, where it's the optimal value for J0. And I increase the epsilon or the external noise of the MBP. And what's the maximum degree to which I can increase epsilon without reducing the reward that it gets by more than alpha? So a theta star with a higher value of epsilon star would be a more robust policy. And of course, a one with a lower value of epsilon star will be a more fragile policy. And again, the story that we're trying to tell is that we don't have access to epsilon star. We can't actually calculate it because we don't have access to J epsilon because J epsilon for epsilon greater than 0 is the kind of like out of distribution environment. So the interesting thing to see is whether this information can be extracted from J0 only. And the claim is, yes, you can actually do that. And in fact, epsilon star takes on a very specific formula. So epsilon star is equal to 1 over 1 plus c lambda, where lambda is the non-zero eigenvalue of the Hessian of J0 at theta star. And c is some constant that depends on alpha, which is very interesting. So the proof for this is pretty simple, which I'm not going to go over. So you just have to calculate the analytic form of J epsilon, and this is possible because the MDP is like very simple. It's just a two-state MDP. Um, and this result does make intuitive sense according to the picture we had earlier with like Bayesian broadness, because if lambda is small, it means that the critical point is kind of flat, and that should correspond to a notion of robustness. So smaller lambda does lead to a greater value of epsilon star. So this does validate our uh, thesis somewhat. And the intuitive reason could be thought of as something like this. So you have S1 and S2, and you have the J function and the parameters theta. I'll just make it a 1D. So given some optimal parameter, optimal parameter theta star, um, all the optimal parameters, the policies they implement behaviorally always stays at S2. But if you slightly perturb the parameter, like by like some delta theta, then you'll be changing the value of theta 1 and theta 2 infinitesimally, which will make it so that there's like a non-zero chance that the policy will accidentally move to S1, even though here it'll deterministically stay at S2. Which in turn means that if you have a flat direction where the value of J doesn't really change despite moving in delta theta, this means that this theta star is the kind of policy where even if it accidentally moves to S1, it can immediately error correct. And that's why a flat direction indicates that the original optimal policy, theta star, is more robust. And in contrast, if you have like a sharper one, then this tells us that theta star is the kind of policy such that if it accidentally goes to S1 by perturbing it a little bit, perturbing the parameters a little bit, then it's not going to be able to recover. So its J value will drop really fast, which will mean a sharper Bayesian, which will mean a larger value of lambda. So this model is some very kind of preliminary and toy validation for the thesis of structural Bayesianism in the context of control. But in some sense, this model is a bit too toy. So because it isn't really about like sequential decision making, where the actions that you make right now affect the decisions or the states that you'll observe in the future. So a second toy model is a tree maze model, which I'll describe now. So so this is intended to be like a abstraction of a sequential decision-making process, where you start from the top node of the tree, and every time step you move downward layer. So the actions that you can take are left and right. And a policy has this sort of like a receptive field where it can only see the two immediate child nodes on the tree, where the nodes take on a value of a 0 or 1. And I'll call those L and R, lowercase. And these values represent the probability that there will be that this node will be a reward state, or the probability that L or R will be equal to 1. And so I call the reward state actually like a cheese because I was motivated initially by the tree maze, like kind of the cheese maze example from the goal misgeneralization literature. So I'll be talking of cheese often. So conceptually, epsilon here kind of represents the in-distribution environment that we have empirical access to. So when epsilon is 0, this value will be 0 and this will be 1. So this means that the cheese will always be at the left of the starting state. And if there is a cheese on the node, and if the policy does reach towards it, then it'll be an absorbing state, so the episode terminates. So here, when epsilon is equal to 0, behaviorally, the optimal policy would be to always move left and have the episode terminate. When epsilon's not 0, and maybe when epsilon is 1 or 1/2 or like something that's not 0, then the optimal policy is, well, if the epsilon is 1, then the optimal policy will be to go right. Oh, sorry, when epsilon is 1, then there's 1/2, 1/2, so it doesn't really matter. But when epsilon is 0, the optimal policy behaviorally is to always move left. And the policy is parameterized by S1 times S1 times like a product of the circles. And the reason I did this instead of interval is because there are some differentiability issues, but you can ignore that. So kind of way to think about the policy parameterization here is kind of like an abstraction of a neural network where L and R are kind of this, or at least in the story that we're trying to tell, L and R are supposed to be like these high-level features that the neural network has already learned to make decisions based off. And theta 1 and phi 0, phi 1, and phi 2 are, well, and these are like bias terms and like weight terms, and they're kind of trading off how we should care about these features. And that determines the probability of going left given L and R and the probability of going right given L and R. So under this setup, as we mentioned earlier, the optimal policy is to always move left. So the optimal parameters in this case form a two-dimensional subtorus of the parameter space. And you can actually see that by just plugging it in, where it says that the probability of moving left at given L1 and R0 is 1, which would make it always move left. Uh, but again, as in the two-state toy model, the important thing is that different parameters of the subtorus implement qualitatively different policies that internally use the high-level features in a different way. Uh, so when phi 0 and phi 1 and phi 2 are all 0, then the policy would be to go left regardless of the input L and R. But if it's 0, 0 pi or pi pi 0, then the policy would be to go left if L is 1 and R is 0, and go right if L is 0 and R is 1. And this represents the policy that actually seeks the cheese instead of just merely moving left. So again, the question is then whether so even though these policies are indistinguishable in terms of the reward that they actually achieve, the question is whether they can be distinguished at the level of the local geometry. So once again, we have a very similar kind of operationalization of this idea, where given theta star, a critical point of J0, we can define epsilon star as a value that solves for this inequality, which represents the degree of out of distribution perturbation that the policy is robust against, or robust against meaning it doesn't decrease the value by the reward by more than alpha. So the same question is whether the local geometry of J0 at theta star encodes this information. And the answer again is yes. So the claim is that epsilon star is now inversely proportional to lambda, where lambda is the non-zero eigenvalue of the Hessian of J0 at theta star, where C prime is some constant. And so we have the same result. And I think the intuition that this example provides is a bit more interesting. So what's the intuitive story that we can tell about why the local geometry encodes this information? And the kind of insight is that so if you have again, that's same as before, if we have a J function and some parameter theta, say the optimal policy here, theta star is the one that always implements going left, so I can kind of like visualize the trajectory as always going in some particular way. But if I perturb the parameters to be of a different value, then it would kind of encounter a different set of trajectories. And that is because the states that you observe are downstream of the actions that you take, which are in turn downstream of the policy, which are in turn downstream of your actions, downstream of your parameters, theta. So if you perturb your theta, then that'll result in you changing the kind of action that you will take, and therefore observing kind of new trajectories or new kind of situations that you wouldn't have seen otherwise. So this kind of represents visually kind of a divergence of the trajectory or the context, which means that a flat direction essentially says that theta star is robust to seeing the kind of situations that it observe when its actions are perturbed in the way implied by perturbing the weights. And the important point is that there's this sort of duality where this flat direction tells us that even if we keep theta star unperturbed, we can keep the theta star unperturbed, but instead kind of dually perturb the MDP, for example, its transition kernel, such that theta star with its unperturbed weights observe exactly the kind of trajectories or situations that it would have observed in its perturbed version. And from the information that there is a flat direction, we know that this is precisely the kind of perturbations to the environment that the policy is robust against. So that is interesting because from this, we now have seen that flat directions in the lost landscape can tell us about precisely what kind of out of distribution perturbations to the environment that the policy would be robust against. And here's an intuition pump. Oh, and I noticed that my iPad is draining the battery from my laptop, so I'll be sharing my laptop instead. Just a second. Okay, okay, so here's an intuition pump. Um, you can imagine an example where you're a human and you're performing some control task, an MDP, and you're receiving some input from the world and it's processed by your visual cortex that is parameterized by theta, and you make some decisions. And suppose that there is a flat direction in your metaphorical reward space, where if I perturb the visual cortex by an infinitesimal amount, such that, say, like you perceive the color or like the hue of the world in a slightly different way, and you still are able to perform your task very well, then this kind of dually means that I can leave your visual cortex unperturbed and instead perturb the world to be of a different color, like change the world to be of a different hue and leave your parameters unperturbed. And the earlier flat direction would then imply that you would still be robust against this kind of perturbations to the environment, which is cool because this is a very concrete example where like intuition pump of like how the flat directions tell you about the kind of out of distribution situations that you'll be robust against. So this is worth kind of like at least formalizing it crudely or like providing like a sketch of. So I think a good way to think about this kind of duality is a sort of emulation principle, where given a perturbation to the input delta x, it is being emulated by a perturbation in the parameters of the model delta theta, which means that this equality holds, where you can where essentially you're kind of push forwarding a perturbation in the x to a perturbation in the parameter, which and you can say it holds for like some class of theta and x. And a concrete model would be something like the following. So you might consider an exponential family model class where the probability. I'll just be mentioning that we'll be for now kind of setting aside the control like MDP stuff because I think this intuition is even though it first came from the control example, I think applies a bit more generally. Uh, so we can consider an unsupervised like distribution modeling task where we have an exponential family model class where the probability of x is proportional to the exponentiation of the inner product between the parameters and t of x, where t is kind of to be interpreted as a fixed feature map of your neural network. And if you assume that there is some group G under which the feature map is equivariant under, which means that there exists a linear representation rho from G to the GLRD, such that such that T of G of X is equal to rho of GT of X, then this implies that we have this formula where the probability of Gx is equal to the probability of X, but the parameters kind of perturbed in this way. So this is a precise example of this kind of emulation principle where a perturbation in the input can be pushed forward to a perturbation in the parameters. And I think this is interesting because it sheds some light on how we can think about the way this sheds some light on how like we should or we could think about the way in which structure and data influences the local geometry of the critical points of a given loss function. So we can consider the same exponential model as earlier, where the probability of x is proportional to this term. And now suppose that the true distribution q of x is g invariant, which means that q of g of x is g of q of x. and assume that the true distribution is in fact realizable, which means Q is equal to P of theta star for some theta star. And then the claim is then that P of x given theta would be equal to P of x given rho g star theta, which is an example of a degeneracy. And the proof is very trivial. Because Q of g x is equal to g of Q of x, and Q is equal to P of theta star, then that means from the earlier formula, we can replace this with P of x given theta, or theta star. So that would be an example of a degeneracy in the parameter space being implied by the data structure and this kind of G equivariant structure of your of the feature map. And one implication of this is that if G is a Lie group, which is like a continuous group, then the rank upper bound of the RLCT decreases by some factor of the dimension of the Lie group. And this is a easy consequence of this fact here, where this decreases the rank of the Hessian by some factor of the Lie group's dimension, which in turn decreases the upper bound of the RLCT. So this is interesting because it is a concrete example of structure in the data implying something about the local geometry of the loss landscape degeneracy. And there are ways to make this kind of point a bit more realistically, where one thing that's unrealistic about the setting is that the symmetries here are kind of generic in the sense of because T does not depend on the parameters at all, this equivariance essentially holds for all values of theta, but that's not like that in practice. So we can consider the case, some example where the exponential model earlier has T now depend on theta too, but importantly, whether T exhibits G equivariance or not depends on the specific values of theta too. You can kind of implement this, you can kind of like think of this as like a theta being like a transformer and theta 2 being the thing that implements some sub-circuit, sub-module of the transformer performing some task that is invariant under some group action, like a protein modeling task that is like invariant under some rotation group. And theta 2, which implements some sub-circuit of this model, kind of determines whether that sub-circuit that it implements will be actually rotation equivariant or not. So if we have two optimal parameters, theta star and theta prime star, but theta star makes T G equivariant, while theta prime star does not, then that'll make it so that the rank upper bound of the RLCT for the former is lower than that of the latter. In other words, this suggests that the Bayesian posterior favors models that makes predictions for the right reasons, or in this specific example, it kind of suggests a way in which the Bayesian posterior could favor models whose internal structure mirrors the symmetry of the data distribution, even though they actually perform identically well in distribution. So this is an example of structural Bayesianism. So to conclude, to kind of recap what we did so far, we did some initial validation of the structural Bayesianism thesis in the control setting by having two toy models, the simple two-state model and a tree maze model, where the core insight was something like flat directions in the J landscape will give us information about the kind of novel situations that the model is robust against, which dually implies what kind of out of distribution perturbations to the MDP that the model is now robust against. And we try to abstract this insight that we got from the tree maze model into a more general setting beyond control by this emulation principle, for which a concrete example was the notion of G equivariant feature maps, and which as an application could show the role the data structure plays in loss landscape degeneracy. And in turn, this kind of provided a plausible story for why models whose internal structure mirrors the data distribution might be favored by the Bayesian posterior. So there are some next steps, which so first we can like kind of try to come up with a concrete instantiation of this with an actual group, with an actual group representation instead of like making it very like abstract like earlier. And the next obvious thing to do is to kind of like bring it down to the control example, like the first two toy models. And kind of an obvious way to do this is assume that there exists an optimal policy pi star that is behaviorally G equivariant. meaning this, and assume that the optimal policy is in fact realizable by some theta star. And this whole setup would then exactly mirror the unsupervised example that I gave earlier. But this does feel kind of artificial because uh, a more natural way we usually think about MDPs and control problems it is in terms of the MDP structure itself, like the structure of the transition matrix, a transition kernel, and the reward kernel. So a more natural thing to do is to put some sort of G symmetry in the MDP structure itself and see whether it implies any of the thing that we showed in the unsupervised case. And kind of going at a more higher level, it'd be interesting to show further examples of structural Bayesianism in the control setting, where maybe some hierarchical structure of the true distribution implies that models whose internal structure somehow mirror this hierarchical structure gets favored by the Bayesian posterior. And coming up with a concrete model of that would be pretty nice. And also, it'd be nice if we could show, come up with some toy models where higher derivatives of the J function provide more fine-grained information about the policy properties and internal structure, which we know is possible because the paper that I mentioned earlier, the programs of singularities, does come up with an example of this where higher derivatives of the potential kind of tell information, at least in the specific uh, model that they provided uh, precise information about the degree of error correction that the Turing machine can perform. So higher derivatives of the Taylor series of the potential vanishing implied some sort of like higher degree of error correction. So it'll be interesting if there are like some higher derivative information in the control case that could say something about the control policy. So yeah, I think that's pretty much it. Thank you.
Hey Darcy, thank you for the talk. If you think of like this is just an informal question, but with regards to those selection theorems you had on like a very early slide, do you think your perspective should indicate that like our agents are more coherent in the ways described by those coherence theorems?
What do you mean more? You mean like behaviorally or?
Yeah, like you should expect them to be more like VNM um in terms of their implementation.
Uh, I don't know. I mean, there is some reason to expect. Well, I mean, the reason why we want to show like agent-like structure problem in the first place is because we have some like intuitive reasons to expect real agents to actually have this kind of modular structure in terms of like an internal world model and a search process. The intuitive reason being, um, well, I guess like the my favorite example is the paper Robust Agents Learn Causal World Model, where if you have an agent that kind of does well under like various interventions to the environment, that kind of implies by backwards induction on the base net variables that like the agent should have some like representation of the world model structure in some behavioral sense that I won't make it precise right now. So I mean, so there are like intuitive reasons to expect this to be the case in the first place, that the agents actually decompose into internal world model in the search process. So yeah, I guess there are like a priori reasons to expect, but not necessarily like the results that I showed so far, like showing that this is like in particular the case. So it'd be nice
Yeah.
to like actually formalize that.
And another question is like, do you have any examples which are like less toy than the ones in the talk?
No.
Okay. Do you think this is like feasible to run experiments on?
Well, I mean,
Like
it's
like
a
real
it's a
games like Pong or something like this?
I am working with the RL group in Timaeus, and they're running experiments, but the experiments that are running are importantly not 2-parameter, 3-parameter models, and they're running larger models. So um, I guess the main value of these toy models aren't to exactly replicate the toy model by PyTorch and like actually run it, but rather kind of give reasons as to why we should expect a correspondence like this in the first place.
Yep.
Yeah.
Okay. All right. That's all for me. There's no more questions then. All right, thank you, Dalcy.